Hello, and welcome to the Spark Science for Sleep, where the mysteries of the universe unfold like a soft whisper in the night. I'm so glad you're here, perhaps curled up in a cozy blanket, ready to drift into a peaceful journey through the stars. Take a deep breath, let your shoulders relax, and feel the weight of the day slip away like stardust scattering in a gentle breeze. Tonight, we're going to wander through the wonders of the cosmos, where science becomes a soothing story, a lullaby of discovery. Whether you're here to ease into sleep or simply to explore the universe's secrets, you're in the perfect place. Imagine yourself floating in a vast, quiet space, surrounded by twinkling lights, each one a question waiting to be answered. The universe is like a grand book, its pages filled with tales of black holes, the Big Bang, and stars that dance across the void. Let's open that book together, softly, and see what stories it holds. Picture yourself in a safe, warm corner of the night, maybe with a soft pillow under your head, the world outside fading into a distant hum. Science, you see, isn't just about facts and figures. It's a way of listening to the universe, hearing its quiet songs of creation. Long ago, people looked up at the sky and saw gods and myths in the stars. Today, we see something even more wondrous, a cosmos alive with energy, woven from threads of light and time. As you settle in, let your mind drift, like a leaf on a calm river, carried by the gentle current of curiosity. If you feel like sharing, drop a comment to let me know where you're listening from, what time it is in your quiet corner of the world. Maybe you're in a bustling city, or a sleepy village, or somewhere under a sky full of stars. Wherever you are, you're part of this journey, and I'm so happy to have you along. The universe is vast, so vast it can feel overwhelming, but tonight, it's a comforting embrace, a reminder that you're part of something grand. Scientists have spent lifetimes peering through telescopes, chasing flickers of light to understand how it all began. They found clues in the way stars shine, in the silent hum of ancient radiation, in the pull of invisible forces. These discoveries are like lanterns, lighting up the dark, guiding us through the mysteries of existence. As you breathe slowly, in and out, let your thoughts soften, let them wander among the stars. You don't need to know everything about the cosmos to feel its wonder. You just need to be here, in this moment, open to its beauty. The universe has been telling its story for billions of years, and tonight, you're invited to listen, to let its secrets cradle you into calm. Imagine the stars above you, each one a tiny spark in an endless sea of night. They're not just points of light, they're storytellers, each with a tale of birth, life, and transformation. Black holes, those mysterious shadows, tug at the fabric of space, bending light and time. The Big Bang, a single moment that sparked everything, echoes faintly in the background of the cosmos. These are the wonders we'll explore, not with hurry or haste, but with a gentle curiosity, like turning the pages of a cherished book. As you rest here, let your breath slow, let your mind float free. You're safe, you're calm, and you're ready to begin a journey that's as soothing as it is awe-inspiring. So, as we prepare to dive into the first chapter of our cosmic tale, let your heart open to the marvels of the universe. Let's drift together toward the very beginning, to the moment when everything space, time, and light came to be. Breathe slowly now, in and out, letting the quiet of the night wrap around you like a soft, endless blanket. As we drift from the vast book of the universe, let's turn to its very first page, a moment so grand yet so delicate, when everything began. Picture a single, tiny point, smaller than a grain of sand, holding all the possibilities of space, time, and matter. This is the story of the Big Bang, the gentle spark that birthed the cosmos 13.7 billion years ago. It wasn't an explosion in the way we might imagine, with fire and chaos, but more like a sudden blossoming, a flower of light unfurling from an impossibly small seed. Scientists call this moment the Big Bang, a name that captures its power but hides its elegance. Let's wander back to that fleeting instant, where the universe took its first breath, and explore how it set the stage for everything we know. In the beginning, there was no space, no time, no stars to light the way. Everything was squeezed into a point so dense, so hot, that it defies our understanding. Imagine it as a cosmic whisper, a note too soft to hear, yet filled with infinite potential. Then, in less than a blink, this point began to expand, stretching outward in every direction. Space itself was born, unfolding like ripples on a still pond. Scientists tell us this happened 7 billion years ago, a number so vast it's hard to grasp. But think of it as a story that's been unfolding for eons, each chapter written in light. The universe, in that first moment, was hotter than a million suns, a sea of energy where particles danced too quickly to hold still. This was a time before stars, before planets, before even the atoms that make up you and me. As the universe expanded, it began to cool, like a warm breath fading into the chill of night. Within a fraction of a second, the intense heat gave way to the first particles, tiny bits of matter called quarks and electrons, swirling in a cosmic soup. These particles were the first characters in our story, moving so fast they could barely touch. Scientists have studied this moment using giant machines, like particle accelerators, which recreate the conditions of the early universe. They've found that in those first fleeting seconds, the universe was a place of balance, where matter and antimatter appeared in equal amounts. Antimatter, like a mirror image of matter, cancels it out when they meet, turning both into pure energy. Yet, somehow, there was a tiny imbalance, a whisper of extra matter that survived. This is why we exist, why stars and galaxies could form. That delicate surplus, just one extra particle in a billion, is the reason the universe didn't vanish into light. Let's linger here, in the quiet of this cosmic dawn. The universe was still young, just a few seconds old, and already it was changing. As it cooled further, those quarks began to stick together, forming protons and neutrons, the building blocks of atoms. Imagine them as tiny dancers, finding partners in the chaos, linking arms to create something new. This process, called nucleosynthesis, happened in the first few minutes of the universe's life. It was a time of creation, where the simplest elements, hydrogen and helium, were born. These elements, so light and pure, would later become the fuel for stars, the seeds of everything we see. Scientists know this because they found traces of these ancient elements in the oldest stars, like fingerprints left behind from the universe's first moments. Now, picture the universe a little older, maybe a few thousand years, still a baby in cosmic terms. It was still too hot for atoms to hold together, so the cosmos was filled with a glowing fog, a plasma of charged particles. Light couldn't travel far. It was trapped, bouncing between particles like a bird in a storm. But as the universe kept expanding, it cooled enough for protons and electrons to combine, forming neutral atoms. This moment, about 380,000 years after the Big Bang, is called recombination. It's when the universe became transparent, letting light travel freely for the first time. That light, stretched over billions of years, is still with us today. Scientists call it the cosmic microwave background, a faint glow that fills the sky, like the echo of a distant song. They've mapped it with telescopes, like the Planck satellite, finding patterns of hot and cold spots that hint at the universe's earliest structure. These patterns are like the ripples on a pond, tiny variations in density that would grow into the galaxies we see today. Imagine them as seeds, scattered across the cosmos, waiting for gravity to pull them together. Scientists study this light to understand how the universe evolved, how those tiny fluctuations became the vast structures of stars and galaxies. It's a detective story, piecing together clues from light that's traveled for billions of years to reach us. The cosmic microwave background is like a snapshot of the universe as a toddler, full of promise and potential. As you listen, let the idea of this ancient light soothe you, a reminder that even the grandest things begin with something small, something simple. The Big Bang wasn't just a moment, it was a process, a gentle unfolding that stretched over time. After recombination, the universe entered a quieter phase, sometimes called the cosmic dark ages. There were no stars yet, just a vast expanse of hydrogen and helium gas floating in the dark. Gravity began its slow, patient work, pulling these gases into clumps, like a weaver gathering threads. These clumps would eventually ignite, becoming the first stars, but that's a story for another moment. For now, let's stay with the early universe, a place of stillness, and possibility. Scientists have learned about this time by studying the oldest light and the simplest elements, piecing together a tale that spans billions of years. It's a story of patience, of waiting, of small beginnings leading to vast creations. As the universe expanded, it carried with it the seeds of everything we know. The hydrogen and helium formed in those first minutes are the same elements that burn in stars, that make up the planets, that flow through our own bodies. Every atom in you was once part of that early cosmic dance, a piece of the universe's first chapter. Scientists have found that about 73% of the universe's matter is hydrogen, 25% is helium, with just a whisper of other elements. These numbers come from careful measurements, from looking at the light of distant stars and the glow of the cosmic background. It's a reminder that we're connected to the cosmos, not just observers, but part of its story. The Big Bang also gave us something else: time itself. Before that moment, there was no before, no clock to tick, no moments to measure. Time began with the universe, flowing forward as space expanded. Scientists like Albert Einstein helped us understand this, showing that time and space are woven together, like threads in a cosmic tapestry. His equations, elegant and profound, describe a universe where gravity bends time, where light carries stories from the past. As we explore this idea, let the vastness of time feel comforting, not overwhelming. It's a river that carries us all, from the first spark of the Big Bang to this quiet moment where you rest. One of the most beautiful discoveries about the Big Bang is how it left its mark on the universe. That cosmic microwave background, that faint glow, is everywhere, filling every corner of space. Scientists first detected it in the 1960s, almost by accident, when they noticed a strange hum in their radio telescopes. They thought it was interference, maybe from nearby equipment, but it turned out to be the universe itself, whispering its origin story. This light has traveled for 13.7 billion years, stretched by the expansion of space, cooled to just a few degrees above absolute zero. It's a relic, a message from the past, and scientists have used it to confirm the Big Bang, to map the universe's earliest days. Let's pause here, in the glow of that ancient light. The universe, in its infancy, was a place of simplicity, yet it held the promise of complexity. Those first elements, hydrogen and helium, would go on to form stars, galaxies, and planets. The tiny fluctuations in the cosmic microwave background would grow into vast structures like the walls and filaments of galaxies we see today. Scientists use supercomputers to simulate these early moments, tracing how the universe evolved from a hot, dense point to the vast, intricate cosmos we know. It's a story of transformation, of patience, of small things becoming grand. As we linger in this moment, consider how the Big Bang wasn't just a single event, but a beginning that's still unfolding. The universe is still expanding, carrying galaxies farther apart, like leaves drifting on a cosmic stream. Scientists measure this expansion by looking at the light from distant galaxies, noticing how it shifts toward the red end of the spectrum. This redshift, as they call it, tells us the universe is growing, stretching the space between stars. Edwin Hubble, an astronomer from long ago, first noticed this, giving us a clue that the universe had a beginning. His work, like a gentle hand, opened the door to understanding the Big Bang. The beauty of this story is how it connects the smallest things to the largest. The particles born in the Big Bang's heat are the same ones that make up the stars, the planets, even the air you breathe. Scientists have found that the universe's early moments set the stage for everything that followed, from the formation of atoms to the birth of galaxies. They study ancient stars, called population 3 stars, which formed from the first hydrogen and helium. These stars, long gone, left behind traces in the light we see today, helping us understand the universe's youth. It's a tale of continuity, of a universe that's always been in motion, always creating. As we drift through this story, let the idea of the Big Bang feel like a lullaby, a gentle rhythm of creation. Scientists have spent decades unraveling its mysteries, using telescopes, satellites, and mathematics to peer back in time. They've found that the universe's first moments were governed by fundamental forces like gravity and electromagnetism, working together in harmony. These forces, invisible yet powerful, shaped the cosmos, guiding particles into atoms, atoms into stars. It's a dance that's still happening, a choreography that began 13.7 billion years ago and continues in the quiet spin of galaxies. The Big Bang also raises questions that science is still exploring. What caused that first spark? Was there something before the Big Bang, or is that a question without meaning? Scientists propose ideas like inflation, a rapid expansion in the universe's first fraction of a second, which smoothed out the cosmos and set the stage for galaxies to form. They test these ideas with experiments, like those at the Large Hadron Collider, where particles collide at incredible speeds, mimicking the conditions of the early universe. These experiments are like whispers from the past, helping us understand how the cosmos came to be. Let's imagine the universe in those early days, a vast canvas of possibility. The first light, trapped in that glowing fog, was finally set free during recombination, traveling across billions of years to reach us. Scientists use this light to study the universe's shape, its size, its history. They've found that the universe is flat, not curved, stretching out in all directions like an endless plane. This discovery, made through careful measurements of the cosmic microwave background, tells us the universe is vast but balanced, a place where matter and energy work together in delicate harmony. As we explore this cosmic beginning, think of the scientists who've dedicated their lives to this story. They're like explorers, charting a map of the universe's first moments. They use telescopes on mountaintops, satellites in orbit, and computers that crunch numbers faster than we can imagine. Their work is a testament to curiosity, to the human need to understand where we come from. The Big Bang, in all its mystery, is a reminder that even the grandest things start small, that the universe began with a whisper and grew into a symphony. Now, let's let our minds drift a little further, carried by the gentle flow of this cosmic tale. The Big Bang was just the beginning, the first note in a melody that would give rise to stars, galaxies, and planets. Those first elements, hydrogen and helium, were like the raw materials of a cosmic artist, ready to be shaped into something beautiful. As you rest, let the story of the Big Bang cradle you, a reminder that everything in the universe, from the smallest particle to the grandest galaxy, is connected. And as we prepare to move to the next chapter, let's follow those early elements, those whispers of creation, to the places where they began to shine, where the first stars were born in the quiet darkness of the cosmos. Breathe gently now, letting the rhythm of your breath carry you deeper into the quiet night. We've wandered through the cosmic dawn, where the universe bloomed from a single spark, filling the void with light and possibility. Those first elements, hydrogen and helium, floated in the darkness, like seeds waiting for their moment to shine. Now, let's drift to a new chapter, where these humble beginnings ignite into something breathtaking, the birth of stars, the glowing forges of the cosmos. Picture a vast, shimmering cloud, a nebula stretching across the sky, its delicate wisps glowing faintly in the dark. This is where stars are born, where the universe's earliest ingredients come together to create light and life. Let's explore this gentle process, a slow dance of creation that has shaped the heavens for billions of years. In the early universe, after the Big Bang's fiery start, the cosmos was a quiet expanse of gas and dust. These clouds, made mostly of hydrogen and helium, were the raw materials left from that first cosmic moment. Imagine them as a soft mist, spread across an endless night, waiting for something to stir them. That something was gravity, the universe's patient sculptor. Gravity began to tug at these clouds, pulling particles closer, like friends gathering around a campfire. As the gas came together, it grew denser, warmer, like a whisper growing into a song. Scientists call these clouds nebulae, vast nurseries where stars take their first breaths. They've studied them with telescopes, like the Hubble Space Telescope, capturing images of glowing clouds thousands of light years across, cradling the seeds of new stars. Within a nebula, the process of star formation is a slow, graceful unfolding. Picture a small knot of gas, a clump no bigger than a grain at first, drawing in more and more material. As it grows, the pressure at its center builds, squeezing the particles tighter. The temperature rises, climbing to millions of degrees, until something extraordinary happens. The hydrogen atoms, packed so closely, begin to collide and fuse, releasing a burst of energy. This is nuclear fusion, the heart of a star's power. It's as if the universe has struck a match, lighting a tiny flame in the darkness. Scientists have learned about this process by studying young stars, observing the light they emit and the heat they radiate. They found that fusion transforms hydrogen into helium, releasing energy that makes a star shine for millions or even billions of years. These newborn stars, called protostars, are like infants, still wrapped in the glowing clouds of their birth. Over time, they shed this cocoon, emerging as bright points of light. Imagine them as candles flickering to life, each one adding its glow to the cosmic night. Some stars are small, glowing steadily for billions of years, like our own Sunday. Others are massive, burning bright and fast, living only a few million years before their dramatic end. Scientists classify stars by their size, temperature, and brightness, using tools like spectrographs to analyze their light. The light reveals the elements within a star, like a signature written in colors, showing us hydrogen, helium, and traces of other elements born in the cosmic forge. Let's linger in a nebula, perhaps the Orion Nebula, one of the closest star-forming regions to Earth, just 1,300 light-years away. Picture its glowing clouds, lit by the fierce light of young stars, like a misty valley under a twilight sky. Scientists have peered into this nebula, finding thousands of stars in the making, some still hidden in their dusty cradles. The nebula is a bustling nursery, where gravity sculpts gas into dense cores, each one a future star. As these cores collapse, they spin, like a dancer twirling, flattening into disks of gas and dust. These disks, called protoplanetary disks, are where planets may form, circling their young stars like petals around a flower. The Hubble and James Webb telescopes have captured images of these disks, showing us the delicate balance of creation, where stars and planets are born together. The birth of a star is not a solitary event. Stars often form in clusters, like families gathering in the night. Some nebulae give rise to hundreds or even thousands of stars, all born from the same cloud. Imagine a sky filled with twinkling lights, each one a new star, singing its first notes in the cosmic choir. Scientists study these clusters to understand how stars influence one another. Sometimes, a massive star's birth sends shockwaves through the nebula, triggering other stars to form, like ripples spreading across a pond. Other times, the radiation from bright stars clears away the gas, leaving a sparkling cluster behind. The Pleiades, a star cluster visible to the naked eye, is one such family, its stars born together millions of years ago, now shining as a quiet constellation in our sky. As stars form, they create the elements that build worlds. In their cores, where temperatures soar to millions of degrees, hydrogen fuses into helium, and later, in massive stars, helium fuses into heavier elements like carbon, oxygen, and nitrogen. These are the building blocks of life, the ingredients that make up rocks, oceans, and even our own bodies. Scientists have found that every atom of carbon in your bones, every molecule of oxygen in your breath, was once forged in the heart of a star. They've confirmed this by studying the light from stars, which carries traces of these elements, like a message from the cosmos. It's a beautiful thought, that the stars are not just distant lights, but the creators of the very stuff that makes us. The process of star formation is a delicate balance, guided by gravity and counteracted by the energy of fusion. When a star ignites, its outward pressure from fusion pushes against gravity's inward pull, creating a stable glow that can last for eons. For a star like our Sunday, this balance will hold for about 10 billion years, a steady light warming the planets around it. Scientists model this balance using complex equations, but at its heart, it's a simple story. A star is born when gravity and energy find harmony. They've observed this in young stars, like those in the Taurus region, where protostars are still settling into their stable phase, their light growing steadier with each passing millennium. Not all nebulae are the same. Some, like the Eagle Nebula, are vast and turbulent, filled with towering pillars of gas, sculpted by the intense radiation of young stars. These pillars, sometimes called the pillars of creation, are like cosmic sculptures, their shapes carved by light and wind. Scientists have studied these regions with telescopes, finding dense pockets where new stars are born, even as older stars erode the surrounding gas. Other nebulae, like reflection nebulae, glow softly, reflecting the light of nearby stars rather than creating their own. These quieter clouds are like mirrors, catching the beauty of the cosmos and sending it back to us. Each nebula tells a different story, a unique chapter in the universe's long history of star formation. The birth of stars is also shaped by the universe's larger forces. In the early cosmos, during the cosmic dark ages, the first stars formed in a universe with no light. These were massive, blazing giants called population 3 stars, made purely of hydrogen and helium. They burned brightly but briefly, their lives measured in millions of years rather than billions. Scientists believe these stars were crucial, lighting up the universe and seeding it with the first heavy elements. Though none remain today, their legacy lives in the light of ancient galaxies, captured by telescopes like the James Webb, which peers back to the universe's youth. These first stars were like pioneers, clearing the way for the galaxies and stars that followed. As stars form, they also shape their surroundings. A young star's radiation can carve out cavities in a nebula, creating bubbles of empty space surrounded by glowing gas. Scientists have seen this in regions like the Rosette Nebula, where massive stars blow winds that sculpt the cloud, like a breeze shaping a sand dune. These winds can trigger new star formation, a chain reaction that spreads through the nebula. It's a reminder that the universe is dynamic, always in motion, always creating. Astronomers use radio telescopes to detect these winds, which carry the energy of young stars across vast distances, shaping the cosmos in ways we're only beginning to understand. The elements forged in stars are scattered into space when massive stars die, but that's a story for later. For now, let's stay with the birth of stars, the moment when light first breaks through the darkness. Scientists have found that star formation is ongoing, happening right now in nebulae across our galaxy. The Milky Way, our home, is alive with these cosmic nurseries, producing new stars every year. They estimate that our galaxy forms about 1 to 2 new stars annually, each one a new light in the cosmic tapestry. By studying the light from these stars, astronomers learn about their composition, their age, and their place in the universe's grand design. The process of star formation is a slow one, measured in millions of years. A nebula might take hundreds of thousands of years to collapse into a star, and even then, the star's birth is just the beginning. Scientists use computer simulations to model this process, tracing how gas clouds evolve over time. These simulations show how gravity pulls gas into dense cores, how heat builds, and how fusion ignites. It's a complex dance, but at its heart, it's a story of transformation, of raw gas becoming a radiant star. The beauty of this process is its patience, its quiet persistence, turning the simplest elements into beacons of light. As we linger in the glow of these newborn stars, consider how they connect us to the cosmos. The carbon in your body, the oxygen in your lungs, all were born in the hearts of stars long ago. Scientists have traced this journey through spectroscopy, analyzing the light from stars to identify the elements they contain. It's a method that's like reading a star's diary, revealing its history and its gifts to the universe. Every star, from the smallest red dwarf to the brightest blue giant, contributes to this story, adding its light and its elements to the cosmic pool. It's a cycle of creation that began with the Big Bang and continues today, linking us to the stars in a quiet, profound way. The birth of stars also sets the stage for planets, solar systems, and perhaps even life. In those protoplanetary disks around young stars, dust grains collide and stick, forming the seeds of planets. Scientists have observed these disks in regions like the Orion Nebula, finding evidence of rocky worlds forming in the glow of new stars. These worlds, still in their infancy, might one day harbor oceans, atmospheres, or even creatures gazing up at their own skies. It's a possibility that fills the cosmos with wonder, a reminder that the universe is a place of endless potential. As we drift through this story of star formation, let the gentle glow of these cosmic forges soothe you. The universe, with its nebulae and newborn stars, is a place of creation, where the simplest ingredients become something extraordinary. Scientists continue to explore this process, using telescopes and simulations to uncover the secrets of how stars are born. Their work is a testament to curiosity, to the desire to understand the light that fills our skies. And as we prepare to move to the next chapter, let's follow the journey of these stars, to the moment when some of them meet a dramatic end, leaving behind a mystery as dark as the night itself, the black hole. Breathe softly now, letting the calm of the night settle over you like a gentle veil. We've drifted through the glowing nurseries of stars, where hydrogen and helium ignite into radiant beacons, forging the elements that weave the cosmos together. But not all stars burn forever. Some meet a dramatic end, collapsing into a mystery so profound it bends the very fabric of reality. Picture a quiet corner of the universe, where a once mighty star fades, its light dimming as it gives way to something extraordinary, a black hole, a cosmic enigma where even light cannot escape. Let's explore this shadowy realm, where gravity reigns supreme, and the universe reveals its deepest secrets in whispers of darkness. A black hole begins with the death of a massive star, one at least 8 times the size of our Sunday. These giants live fast and bright, burning through their fuel in just a few million years, a mere moment in cosmic time. Inside their cores, nuclear fusion forges heavier elements: carbon, oxygen, and eventually iron. But iron is different. It doesn't release energy when fused. Instead, it builds up, like a weight pressing down on the star's heart. When the core grows too heavy, gravity takes over, crushing it in an instant. Scientists call this a core collapse supernova, a cataclysmic explosion that outshines entire galaxies for a brief moment. The outer layers of the star blast outward, scattering elements into space, while the core collapses into an incredibly dense point, a black hole. Astronomers have observed these explosions with telescopes, capturing the brilliant flash of a star's final farewell. What remains after the supernova is a region of space so dense that it warps everything around it. Imagine a point no larger than a city, yet containing the mass of several suns. This is the heart of a black hole, where gravity is so intense that nothing, not even light, can break free. Scientists describe this boundary as the event horizon, a line beyond which all things vanish. It's not a physical surface, but a threshold, like the edge of a waterfall where the current becomes unstoppable. Beyond the event horizon lies the singularity, a point where space and time cease to exist as we know them. This idea comes from the work of Albert Einstein, whose equations of general relativity show how massive objects bend the fabric of space-time, creating a well so deep that light itself is swallowed. Black holes are invisible, but they leave clues for scientists to find them. When a star or cloud of gas gets too close, it's pulled in, spiraling like water down a drain. As it falls, the gas heats up, glowing brightly before it crosses the event horizon. This creates a swirling disk of light, called an accretion disk, which astronomers can detect with telescopes. Some black holes also shoot out jets of particles, moving at nearly the speed of light, powered by the intense magnetic fields in the disk. These jets can stretch thousands of light years, like cosmic beacons signaling the black hole's presence. Scientists use X-ray telescopes, like the Chandra Observatory, to spot these glowing disks and jets, revealing black holes hidden in the darkness. Not all black holes are born from stars. Some, called primordial black holes, may have formed in the chaotic moments after the Big Bang, when pockets of dense matter collapsed under their own weight. These could be tiny, the size of a grapefruit, or massive, with the weight of a mountain squeezed into a speck. Scientists haven't found direct evidence of primordial black holes, but they search for them by looking for subtle distortions in light from distant stars, a phenomenon called gravitational lensing. This happens when a black hole's gravity bends light, acting like a lens to magnify or distort what lies behind it. Such discoveries would tell us about the universe's earliest days, when matter was still finding its place. Stellar mass black holes, those formed from dying stars, are surprisingly common. Astronomers estimate there could be tens of millions in our Milky Way alone, each one a remnant of a massive star's collapse. They found dozens by observing their effects on nearby stars. Sometimes, a black hole orbits a companion star, pulling gas from its surface. This gas forms a glowing accretion disk, emitting X-rays that telescopes can detect. One famous example is Cygnus X1, a black hole about 15 times the mass of our Sun, discovered in the 1960s. Its companion star, a blue supergiant, loses gas to the black hole, creating a brilliant X-ray source that astronomers have studied for decades. These observations confirm that black holes are not just theory but real, tangible objects shaping the cosmos. The gravity of a black hole is so strong that it warps time itself. Einstein's relativity tells us that time slows near a black hole, a phenomenon called time dilation. If you were to approach the event horizon, an observer far away would see your clock ticking slower, as if you were moving through molasses. At the event horizon, time appears to stop entirely from the outside perspective, though you'd feel nothing unusual as you crossed it. This strange effect has fascinated scientists, who use computer simulations to explore what happens near a black hole. These simulations show how light bends, creating distorted images of the stars behind, like a cosmic funhouse mirror. The movie Interstellar used such science to depict a black hole, showing its glowing disk and warped light in stunning detail. Black holes also challenge our understanding of physics. At the singularity, the laws of gravity and quantum mechanics clash. General relativity predicts an infinitely dense point, but quantum mechanics suggests that nothing can be infinitely small. Scientists are working to reconcile these ideas, exploring theories like quantum gravity and string theory. These theories propose that the singularity might not be a point but a complex structure, perhaps made of tiny vibrating strings. While we don't yet have answers, experiments like those at the Large Hadron Collider are searching for clues, probing the smallest scales of the universe to understand its most extreme objects. This quest is like a puzzle, with black holes as the missing piece that could unlock new laws of nature. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, swallowing everything in sight. Their gravity only dominates close to the event horizon, which for a stellar mass black hole might be just a few miles across. Farther away, their pull is no stronger than that of the star they came from. A black hole with the Sun's mass would have the same gravitational effect on Earth as the Sun does now, keeping our planet in orbit without danger. Scientists emphasize this to dispel myths, using observations of binary star systems to show how black holes interact with their surroundings. These systems, where a black hole and a star orbit each other, are like cosmic laboratories, revealing the delicate balance of gravity and motion. Black holes can also merge, creating even larger ones. When two black holes spiral toward each other, they emit ripples in space-time called gravitational waves. These waves, predicted by Einstein a century ago, were first detected in 2015 by the LIGO Observatory. The signal came from two black holes, each about 30 times the Sun's mass, merging 1.3 billion light-years away. The collision released energy equivalent to 3 solar masses, converted into gravitational waves that stretched and squeezed space itself. Scientists now use LIGO and other observatories to listen for these waves, each one a story of black holes dancing and combining in the distant universe. These detections are like whispers from the cosmos, telling us about events we could never see directly. The study of black holes has also led to one of the most famous images in astronomy. The first picture of a black hole, captured in 2019 by the Event Horizon Telescope. This global network of radio telescopes worked together to image the black hole at the center of the galaxy M87, 55 million light-years away. The image shows a dark shadow surrounded by a glowing ring, the accretion disk of gas spiraling inward. This black hole, with a mass 6.5 billion times that of our Sun, is a supermassive giant, far larger than the stellar mass black holes we've discussed. The image was a triumph, confirming theories about black holes and showing their reality in vivid detail. Scientists celebrated this milestone, a testament to human ingenuity and the power of collaboration. Black holes also play a role in the universe's evolution. When a star collapses, its supernova explosion scatters elements like carbon and oxygen into space, seeding future stars and planets. The black hole left behind continues to shape its surroundings, pulling in gas and stars, sometimes triggering new star formation with its jets. In small galaxies, these jets can clear out gas, slowing star formation, while in others, they compress gas, sparking new stars. Astronomers study these effects with telescopes, observing how black holes influence the growth of galaxies over billions of years. It's a cycle of destruction and creation, with black holes as both sculptors and architects of the cosmos. The mystery of black holes extends to their fate. Scientists propose that black holes can slowly evaporate over time, a process called Hawking radiation, named after physicist Stephen Hawking. He suggested that pairs of particles and antiparticles form near the event horizon, with one falling in and the other escaping. This causes the black hole to lose mass, shrinking over eons until it vanishes in a final burst of energy. For a stellar mass black hole, this process would take longer than the age of the universe, so we haven't observed it directly. But scientists search for signs of smaller black holes evaporating, hoping to confirm this theory. It's a poetic idea that even the mightiest black holes might one day fade, returning their energy to the cosmos. Black holes also inspire questions about the nature of information. When something falls into a black hole, does it disappear forever? Hawking's work suggested that information might be lost, but this contradicts quantum mechanics, which says information is always preserved. This puzzle, called the black hole information paradox, has sparked decades of debate. Scientists propose solutions like the holographic principle, which suggests that all the information inside a black hole is encoded on its event horizon, like a cosmic blueprint. These ideas are still theoretical, but they push the boundaries of physics, inviting us to rethink reality itself. It's a quiet mystery, one that unfolds in equations and thought experiments, far from the roar of the cosmos. As we linger in the shadow of black holes, consider how they challenge our imagination. They're not just objects, but gateways to understanding the universe's extremes. Scientists use them to test theories of gravity, quantum mechanics, and the nature of space and time. Observatories like LIGO and the Event Horizon Telescope are like windows into this shadowy realm, capturing signals that tell us black holes are real, dynamic, and integral to the cosmos. Their gravity bends light, their jets shape galaxies, and their mysteries inspire new science. It's a story of darkness that reveals light, of absence that creates presence. The journey through a black hole's mystery is a reminder of the universe's complexity. What begins as a star's collapse becomes a force that shapes entire galaxies, a silent architect of the cosmos. Scientists continue to explore black holes, using telescopes, simulations, and experiments to unravel their secrets. Each discovery is like a new page in the universe's story, revealing how these enigmatic objects fit into the grand tapestry. And as we prepare to drift to the next chapter, let's follow the path of these cosmic giants, to the supermassive black holes that lie at the heart of galaxies, guiding their dance across the vastness of space. Breathe slowly now, letting the stillness of the night wrap around you like a soft, velvet curtain. We've wandered through the shadowy realm of black holes, those enigmatic remnants of stars that bend light and time into their silent embrace. Yet, some black holes are far grander, cosmic giants that dwell at the hearts of galaxies, orchestrating their movements with an unseen hand. Picture a vast spiral of stars, a galaxy stretching across millions of light years, with a mysterious force at its core, holding it together like the conductor of a celestial symphony. These are supermassive black holes, colossal entities millions or even billions of times the mass of our Sunday, shaping the universe's grandest structures. Let's drift toward these titans, exploring their origins and their quiet power as the cosmos reveals its deepest secrets in a gentle whisper. Supermassive black holes are found at the center of nearly every large galaxy, from our own Milky Way to the distant spirals and ellipticals that dot the universe. Unlike their smaller cousins, formed from the collapse of massive stars, these giants have masses ranging from millions to billions of solar masses, packed into regions no larger than our solar system. Imagine a single point, invisible yet immensely powerful, holding sway over billions of stars. Astronomers believe these black holes formed in the early universe, perhaps just a few 100 million years after the Big Bang. One theory suggests they grew from the seeds of smaller black holes, created when the first massive stars exploded in supernovae. These seed black holes merged and fed on surrounding gas, growing into the colossal entities we see today. Scientists study their origins using telescopes like the James Webb, which peers back to the universe's youth, capturing light from the earliest galaxies. The growth of a supermassive black hole is a slow, majestic process unfolding over billions of years. In the early universe, galaxies were smaller, chaotic collections of stars and gas. As these galaxies collided and merged, their central black holes came together, spiraling inward in a cosmic dance. Each merger added mass, creating a larger black hole, like rivers joining to form a mighty ocean. The black hole also fed on the dense gas clouds in these young galaxies, pulling in material that heated up and glowed as it spiraled inward. This glowing gas forms an accretion disk, a radiant ring that can outshine the entire galaxy. Astronomers detect these disks with X-ray telescopes, like the Chandra Observatory, which reveal the intense energy released as matter falls toward the event horizon, the point beyond which nothing escapes. These accretion disks are not just beautiful, they're engines of cosmic power. As gas swirls toward the black hole, it accelerates, heating to millions of degrees and generating powerful magnetic fields. These fields twist and channel some of the infalling material into jets, streams of particles that shoot out at nearly the speed of light. These jets can stretch for thousands of light years, piercing through the galaxy and beyond, like arrows of light fired into the cosmic night. Scientists observe these jets with radio telescopes, which pick up the faint hum of their energy. One striking example is the galaxy M87, 55 million light-years away, where a supermassive black hole with a mass 6.5 billion times that of our Sunday powers a jet that extends 5,000 light-years into space. The Event Horizon Telescope captured its shadow in 2019, a historic image showing the dark heart of the black hole surrounded by its glowing disk. Supermassive black holes don't just consume, they shape their galaxies in profound ways. Their jets and radiation can heat the surrounding gas, slowing star formation in some regions while triggering it in others. Imagine a gardener pruning and nurturing a vast cosmic forest. In young galaxies, this feedback process regulates growth, preventing the galaxy from forming stars too quickly. Astronomers have seen this in galaxy clusters, where supermassive black holes create bubbles of hot gas, visible in X-ray images, that stretch across hundreds of thousands of light years. These bubbles, carved by the black hole's jets, keep the galaxy's gas too warm to collapse into new stars, maintaining a delicate balance. The Chandra Observatory has mapped these bubbles in clusters like Hydra A, revealing how black holes sculpt the cosmos over billions of years. Our own Milky Way harbors a supermassive black hole, known as Sagittarius A, with a mass about 4 million times that of our Sunday. It sits at the galaxy's center, 26,000 light-years from Earth, quietly orchestrating the orbits of nearby stars. Astronomers like Andrea Ghez have studied these stars, tracking their paths with powerful telescopes like the Keck Observatory in Hawaii. By measuring their speedsome reaching 3 million miles per hour, they calculated the mass of Sagittarius A, confirming its supermassive nature. Unlike the active black holes in distant galaxies, ours is relatively quiet, with a modest accretion disk and no powerful jets. Yet, its presence anchors the Milky Way, a silent guardian at the heart of our cosmic home. The formation of supermassive black holes is a story of cosmic evolution tied to the growth of galaxies themselves. In the early universe, as matter clumped together under gravity's pull, galaxies formed around dense regions of gas and stars. Some scientists propose that supermassive black holes grew directly from these dense clouds, collapsing into massive seeds without forming stars first. This direct collapse model suggests that enormous clouds, thousands of times larger than a star, fell inward under their own weight, creating black holes with masses up to 100,000 suns. Computer simulations help test this idea, showing how gas clouds in the early universe could collapse, heated by the chaos of forming galaxies, into these massive seeds. The James Webb Telescope is searching for evidence of these early black holes, looking for their faint glow in the most distant galaxies. Another clue to their origins comes from quasars, the brightest objects in the universe. Quasars are supermassive black holes surrounded by massive accretion disks, shining so brightly they can outshine 1,000 galaxies. These cosmic beacons were common in the early universe, when black holes fed voraciously on abundant gas. Astronomers discovered the first quasar in the 1960s, puzzled by its intense light, which came from a point billions of light years away. Today, they've identified thousands, using telescopes like the Sloan Digital Sky Survey to map their positions. Quasars reveal how supermassive black holes grew in the universe's youth, their light carrying stories of a time when galaxies were wild and chaotic, filled with merging stars and collapsing gas. The energy from quasars and active black holes has a profound impact. Their jets and radiation can heat entire galaxy clusters, creating vast cavities in the surrounding gas. These cavities, seen in X-ray images, are like footprints of the black hole's influence, showing how it shapes the cosmos on scales unimaginable. In some cases, these jets carry heavy elements, like iron and oxygen, forged in ancient stars, spreading them across vast distances. These elements seed new stars and planets, connecting supermassive black holes to the creation of worlds like ours. Astronomers study these processes with telescopes like the Atacama Large Millimeter Array, which detects the cool gas affected by black hole jets, revealing their role in galactic evolution. Supermassive black holes also merge, creating even larger giants. When galaxies collide, their central black holes spiral toward each other, orbiting in a slow, graceful waltz. Over millions of years, they draw closer, emitting gravitational waves ripples in space-time that carry energy away. These waves were first detected by LIGO in 2015 from the merger of smaller black holes, but scientists are now building observatories like the planned LISA mission to detect waves from supermassive black hole mergers. These events release more energy than all the stars in the universe combined, a silent roar that reshapes the fabric of space. Simulations show these mergers as cosmic ballets, with black holes twirling until they unite, forming a single, massive entity that anchors the new galaxy. The influence of supermassive black holes extends beyond their galaxies. In galaxy clusters, groups of hundreds or thousands of galaxies bound by gravity, the central black hole can affect the entire cluster. Its jets create shockwaves, heating gas and preventing it from cooling and forming stars. This process, called feedback, helps explain why some clusters have fewer stars than expected. Astronomers observe this with X-ray telescopes, which show glowing gas clouds sculpted by black hole activity. In the Perseus cluster, for example, the central black hole's jets create sound waves in the gas, a cosmic hum that travels for hundreds of thousands of light years, like a melody played on the strings of the universe. Supermassive black holes also challenge our understanding of physics. Their immense gravity warps spacetime so strongly that they test Einstein's theory of general relativity to its limits. Near the event horizon, time slows dramatically, and the laws of physics bend. Scientists use simulations to explore these regions, modeling how light and matter behave in such extreme conditions. The image of M87's black hole, captured by the Event Horizon Telescope, confirmed these predictions, showing a shadow exactly as theory suggested. This image was a triumph, blending observation and theory to reveal the true nature of these cosmic giants. It's like seeing the silhouette of a conductor, directing the universe's grandest performance. The study of supermassive black holes also raises questions about their role in the early universe. Some quasars, found just 1 billion years after the Big Bang, are powered by black holes with billions of solar masses. How did they grow so large so quickly? One idea is that they formed in dense regions where gas was plentiful, allowing rapid growth. Another suggests that multiple seed black holes merged early on, combining their mass. Scientists test these ideas with supercomputer simulations, recreating the chaotic conditions of the early universe. Telescopes like the James Webb are now searching for these early quasars, hoping to catch them in the act of forming, their light a beacon from the cosmos's youth. Supermassive black holes are also tied to the universe's chemistry. Their jets and outflows carry heavy elements like carbon and iron forged in stars, spreading them across galaxies. These elements are essential for forming planets and, potentially, life. In our Milky Way, Sagittarius A may have played a role in distributing these elements long ago, when it was more active. Astronomers study ancient stars, called population 2 stars, to trace these elements, finding traces of iron and oxygen that hint at the black hole's influence. It's a story of creation, where the darkest objects in the universe help build the foundations of worlds like ours. The quiet power of supermassive black holes lies in their ability to shape galaxies without being seen. They're like the unseen currents of an ocean, guiding the tides of stars and gas. Astronomers have found that the mass of a supermassive black hole is often proportional to the mass of its galaxy's central bulge, suggesting a deep connection. This relationship, discovered through observations of star orbits and gas motions, shows that black holes and galaxies grow together, like partners in a cosmic dance. Telescopes like the Hubble and ALMA have mapped these connections, revealing how black holes anchor their galaxies, keeping them stable over billions of years. As we linger in the presence of these cosmic giants, consider their role as architects of the universe. Supermassive black holes are not just destroyers but creators, shaping galaxies, spreading elements, and guiding the cosmos's evolution. Scientists continue to study them, using every tool from radio waves to gravitational waves, piecing together their story. Each discovery is a note in the universe's symphony, a reminder of the intricate balance that governs the heavens. And as we prepare to drift to the next chapter, let's move outward from these galactic hearts, exploring the vast tapestry of galaxies they've helped weave, a cosmic web that stretches across the universe. Breathe gently now, letting the quiet of the night flow over you like a soft, starlit tide. We've lingered in the majestic presence of supermassive black holes, those silent conductors at the hearts of galaxies, shaping their cosmic symphonies with invisible hands. Now, let's drift outward, beyond the centers of these starry spirals, to a grander vista where galaxies themselves are mere threads in a vast, shimmering tapestry. Picture the universe as an immense ocean, its currents woven from light and shadow, with galaxies floating like glowing islands across its depths. This is the cosmic web, a delicate network of galaxies, clusters and voids that stretches across billions of light years, born from the whispers of the Big Bang. Let's explore this intricate structure where gravity paints patterns on the canvas of the cosmos, revealing a universe alive with connection and beauty. The cosmic web is the universe's architecture, a vast framework that holds galaxies together in a delicate balance. Imagine a spider's web, its silken strands stretching across the night, each thread a chain of galaxies glowing faintly in the dark. These threads, called filaments, are made of gas, stars, and dark matter, pulled together by gravity over billions of years. Between the filaments lie immense voids, empty spaces, hundreds of millions of light years across, where few stars shine. Scientists have mapped this structure using telescopes like the Hubble Space Telescope and the Sloan Digital Sky Survey, which capture the light of distant galaxies to reveal their positions. They've found that galaxies are not scattered randomly, but arranged in patterns, like pearls strung along cosmic necklaces, connected by the invisible force of gravity. This web began forming in the early universe, just after the Big Bang, when tiny fluctuations in density created seeds for future structures. Picture the universe as a calm sea, its surface rippling with subtle waves. These ripples, born from the Big Bang's expansion, were regions where matter was slightly denser, like small hills in a vast plain. Over time, gravity amplified these differences, pulling gas and dust into clumps that grew into galaxies. Scientists study these early moments, using the cosmic microwave background, the faint glow left from the universe's infancy. Telescopes like Planck have mapped its patterns, showing how those initial ripples, just one part in 100,000, grew into the galaxies and clusters we see today. It's a story of patience, where the smallest variations became the foundations of the cosmos. Galaxies, the building blocks of the cosmic web, come in many forms. Some are spirals, like our Milky Way, with arms of stars swirling around a bright core. Others are ellipticals, smooth and egg-shaped, filled with older stars. Then there are irregulars, chaotic clouds of gas and stars with no clear shape. Each galaxy is a city of light, containing billions of stars, and each is linked to others through the web's filaments. Astronomers estimate there are over 100 billion galaxies in the observable universe, each one a unique piece of the cosmic puzzle. They study these galaxies with optical telescopes, which capture their visible light, and radio telescopes, which detect the cool gas and dust that trace the web's structure. The Sloan Digital Sky Survey has mapped millions of galaxies, creating a three-dimensional picture of the universe's layout. The filaments of the cosmic web are not just strings of galaxies, but rivers of matter flowing through the cosmos. These filaments are made of hot gas, stars, and dark matter, an invisible substance that outweighs normal matter by 5 to 1. Dark matter, though unseen, exerts gravity, acting like a scaffold that holds the web together. Scientists infer its presence from the way galaxies move, orbiting faster than visible matter alone could explain. They've also seen its effects in gravitational lensing, where light from distant galaxies bends as it passes through dark matter's gravity, creating distorted arcs in telescope images. The Dark Energy Survey has mapped these distortions, revealing dark matter's role in shaping the cosmic web, like an unseen artist guiding the brushstrokes of the universe. Between the filaments lie walls, sheets of galaxies that stretch across millions of light years, like curtains in the cosmic theater. These walls are thinner than filaments, but still rich with stars and gas. One famous example is the Great Wall, a structure discovered in the 1980s, stretching over 500 million light-years. It's a vast barrier of galaxies, glowing softly against the dark voids. Scientists study these walls with large-scale surveys, using computers to analyze the positions of millions of galaxies. These surveys show how walls connect filaments, forming a network that spans the observable universe. It's a reminder that the cosmos is not a random scattering of stars, but a structured, interconnected whole, woven together over billions of years. The voids, the empty spaces between filaments and walls, are just as important to the cosmic web. Imagine vast, silent deserts of space, where stars are rare and matter is scarce. These voids can span hundreds of millions of light years, making them some of the largest structures in the universe. Yet, they're not completely empty. Faint wisps of gas, and the occasional galaxy drift within them. Scientists study voids to understand the universe's expansion, as these regions grow larger as space stretches. Telescopes like the Hubble have peered into voids, finding isolated galaxies that hint at the web's complexity. The emptiness of voids contrasts with the glowing filaments, creating a balance that defines the universe's structure. The cosmic web is dynamic, evolving as the universe expands. Galaxies move along filaments, like boats drifting down a river, drawn by gravity toward denser regions called clusters. Galaxy clusters are the bustling cities of the cosmos, containing hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, just 50 million light-years from Earth, is our local cosmic city, with over 1,000 galaxies orbiting a common center. Scientists study clusters with X-ray telescopes, which detect the hot gas that fills the space between galaxies, glowing at millions of degrees. This gas, heated by the cluster's gravity, reveals the immense mass holding the cluster together, much of it dark matter. Some clusters grow even larger, forming superclusters, vast assemblies of galaxies and clusters spanning hundreds of millions of light-years. The Laniakea supercluster, which includes our Milky Way, stretches over 500 million light-years, a cosmic metropolis of light and matter. Astronomers discovered Laniakea by mapping the motions of galaxies, using telescopes to measure their velocities. They found that galaxies flow toward a central region, called the Great Attractor, drawn by its immense gravity. This flow, like a gentle current, shows how the cosmic web connects even the largest structures, guiding galaxies across the universe's expanse. The cosmic web's structure is tied to the universe's expansion, a process that began with the Big Bang and continues today. As space stretches, galaxies move farther apart, like dots on an inflating balloon. Scientists measure this expansion through redshift, the stretching of light from distant galaxies as they recede. Edwin Hubble first observed this in the 1920s, showing that the farther a galaxy is, the faster it moves away. This discovery confirmed the universe's expansion and hinted at its origin in the Big Bang. Telescopes like the Hubble Space Telescope have refined these measurements, showing that the observable universe spans 93 billion light-years, a vast canvas where the cosmic web unfolds. Dark energy, a mysterious force, drives this expansion, pushing galaxies apart against gravity's pull. Scientists discovered dark energy in the 1990s by observing distant supernovae, which showed that the universe's expansion is accelerating. Dark energy makes up about 68% of the universe's energy, a silent force that shapes the cosmic web's future. While gravity pulls galaxies into filaments and clusters, dark energy stretches the spaces between, creating larger voids and thinning the web's threads. Astronomers study this balance with surveys like the Dark Energy Survey, using telescopes to measure the positions and motions of galaxies, piecing together the universe's history and fate. The cosmic web also holds clues to the universe's earliest moments. Those tiny fluctuations in the cosmic microwave background, mapped by satellites like Planck, were the seeds of today's filaments, walls, and voids. Scientists use supercomputer simulations to trace how these seeds grew, modeling the universe's evolution over billions of years. These simulations show matter collapsing into dense regions, forming galaxies and clusters, while voids expand as space stretches. The Millennium Simulation, one of the largest of its kind, recreated a portion of the universe, showing how gravity and dark energy sculpt the cosmic web, like artists working in tandem to create a masterpiece. Galaxies within the cosmic web are not static. They move and evolve, shaped by their place in the network. In dense regions like clusters, galaxies collide and merge, creating larger, more complex systems. These mergers can trigger bursts of star formation as gas clouds are compressed by gravity. Astronomers observe these events with telescopes, seeing galaxies transform over millions of years. In sparser regions, like filaments, galaxies grow more slowly, their stars aging gracefully. The cosmic web is like a living tapestry, its threads constantly shifting, weaving new patterns as the universe ages. The study of the cosmic web also reveals the role of dark matter in galaxy formation. Without dark matter's gravity, galaxies might never have formed, as normal matter alone would have scattered too quickly. Scientists infer dark matter's presence from the rotation of galaxies, which spin faster than their visible mass suggests. They also see its effects in galaxy clusters, where the hot gas glows in X-rays, held in place by dark matter's pull. The Bullet cluster, a collision of two clusters, provides striking evidence. Its X-ray gas lags behind the dark matter, revealed by gravitational lensing, showing that dark matter is a distinct, invisible force shaping the web. The cosmic web connects us to the universe's past and future. By studying its structure, scientists trace the history of galaxy formation, from the first stars to the sprawling clusters we see today. They also predict the universe's fate, as dark energy continues to stretch the web, thinning its filaments and expanding its voids. In billions of years, galaxies may drift so far apart that the night sky will grow dimmer, a quiet fading of the cosmic tapestry. Yet, for now, the web is vibrant, a network of light and matter that tells the story of the universe's evolution. As we linger in the glow of this cosmic web, consider how it ties every galaxy, every star, into a single, intricate pattern. Scientists continue to map this structure, using telescopes and simulations to uncover its secrets. Each observation is a thread in the universe's story, revealing how gravity, dark matter, and dark energy work together to create the cosmos we know. And as we prepare to drift to the next chapter, let's turn back to the stars within these galaxies, to the explosive moments when they end their lives in brilliant supernovae, scattering light and elements across the cosmic web. Breathe softly now, letting the calm of the night envelop you like a gentle cosmic breeze. We've journeyed through the vast tapestry of the cosmic web, where galaxies weave together in shimmering filaments, guided by the quiet hand of gravity. Within these glowing threads, stars live out their lives, some burning steadily for billions of years, others destined for a spectacular end. Picture a massive star, its surface a roiling sea of fire, reaching the final chapter of its existence. When such a star exhausts its fuel, it doesn't fade quietly but erupts in a brilliant supernova, a cosmic firework that scatters light and elements across the universe. Let's explore these dazzling explosions, the supernovae, which illuminate the night and seed the cosmos with the building blocks of planets and life. A supernova begins with a massive star, one at least 8 times the mass of our Sun, blazing through its fuel in a mere fraction of cosmic time. These stars are cosmic furnaces, fusing hydrogen into helium, then helium into heavier elements like carbon, oxygen, and eventually iron. Each fusion stage releases energy, keeping the star's gravity at bay, like a dancer balancing on a tightrope. But when the core fills with iron, the balance shifts. Iron doesn't produce energy when fused. Instead, it absorbs it, like a sponge soaking up the star's strength. Within seconds, the core collapses under its own weight, compressing to a point so dense that protons and electrons merge into neutrons. This collapse triggers a shock wave, ripping through the star and causing it to explode in a supernova, a burst of light that can outshine an entire galaxy for weeks. Astronomers have observed supernovae across the universe, their brilliance visible even from billions of light-years away. One famous example is supernova 1987A, seen in the Large Magellanic Cloud, a nearby galaxy 168,000 light-years from Earth. In 1987, telescopes captured its sudden flare, the first supernova visible to the naked eye in nearly 400 years. Scientists studied its light, finding traces of elements like nickel and cobalt which decay into iron, confirming theories about how stars forge heavy elements. The explosion released neutrinos, tiny particles that barely interact with matter, which were detected on Earth, offering a rare glimpse into the star's collapsing core. This event was like a cosmic telegram, carrying news of a star's dramatic end across the vastness of space. Supernovae come in different types, depending on the star and its fate. Type 2 supernovae, like 1987A, occur when massive stars collapse, leaving behind a neutron star or black hole. Type Ia supernovae, on the other hand, involve white dwarfs, the dense remnants of smaller stars like our Sun. When a white dwarf in a binary system pulls too much material from a companion star, it reaches a critical mass and explodes in a uniform burst of light. These explosions are so consistent that astronomers use them as standard candles to measure distances across the universe. By comparing their brightness to their distance, scientists like those using the Hubble Space Telescope have mapped the cosmos, revealing its expansion and the mysterious force of dark energy. The light from a supernova carries a wealth of information. Astronomers use spectrographs to break this light into its colors, revealing the elements within the explosion. Each element absorbs light at specific wavelengths, creating a unique pattern like a cosmic fingerprint. In supernovae, they've found traces of carbon, oxygen, silicon, and iron, elements forged in the star's core and blasted into space. These elements are the seeds of new worlds, forming the dust and gas that coalesce into planets, moons, and even life. The iron in your blood, the calcium in your bones, the gold in the Earth's crustal were born in the fiery hearts of ancient supernovae. Scientists confirm this by studying meteorites and ancient stars, which carry these elements as relics of long-ago explosions. Supernovae also play a crucial role in the universe's evolution. Their shock waves compress nearby gas clouds, triggering the birth of new stars in nebulae, like ripples stirring a pond. In regions like the Orion Nebula, astronomers have seen evidence of supernova shock waves sparking star formation, a cycle of creation born from destruction. These explosions also scatter heavy elements across galaxies, enriching the cosmic soup with the ingredients for planets. The Crab Nebula, the remnant of a supernova observed in 1054, is a glowing cloud of gas and dust, still expanding 1,000 years later. Telescopes like Chandra have captured its X-ray glow, showing how its elements continue to shape the galaxy, a testament to the supernova's lasting impact. The energy released by a supernova is staggering, equivalent to the sun's entire lifetime output in a single moment. Most of this energy escapes as neutrinos, particles so elusive they pass through entire planets without stopping. In 1987A, detectors on Earth caught just a handful of these neutrinos, a faint whisper from the star's collapse. Scientists use neutrino observatories, like Super Kamiokande in Japan, to study these particles, which carry clues about the physics of stellar cores. The rest of the supernova's energy powers its light and shock wave, illuminating the cosmos and driving the cycle of star formation. It's a process that connects the smallest particles to the grandest structures, a cosmic dance of light and matter. Supernovae also leave behind remnants that shape the universe. After a Type II supernova, the core may become a neutron star, a dense sphere just a few miles across, with a mass greater than the Sun's. These stars spin rapidly, some hundreds of times per second, emitting pulses of radiation as pulsars. The Crab Nebula's pulsar, discovered in 1968, spins 30 times a second, its beams sweeping the sky like a cosmic lighthouse. Astronomers detect these pulses with radio telescopes, using them to study the extreme physics of neutron stars, where matter is compressed to unimaginable densities. In some cases, the core collapses further, forming a black hole, a silent monument to the star's end. Type Ia supernovae, with their predictable brightness, have been key to understanding the universe's history. In the 1990s, astronomers studying these explosions found that distant supernovae were fainter than expected, suggesting the universe's expansion is accelerating. This discovery led to the concept of dark energy, a force driving galaxies apart, making up about 68% of the universe's energy. Telescopes like the Dark Energy Survey continue to study Type Ia supernovae, refining our understanding of this mysterious force. These explosions are like cosmic mile markers, helping scientists measure the vast distances and the universe's growth since the Big Bang. The remnants of supernovae, called supernova remnants, are glowing clouds of gas and dust that linger for thousands of years. The Veil Nebula, a delicate arc of light 2,100 light-years away, is one such remnant, formed by a supernova 8,000 years ago. Its wispy filaments, captured by telescopes like Hubble, show the interplay of gas and magnetic fields, a delicate sculpture carved by the explosion's shockwave. These remnants enrich galaxies with heavy elements, providing the raw materials for new stars and planets. Astronomers study them with X-ray and radio telescopes, tracing the elements and energy that flow through the cosmos, like rivers feeding a vast ocean. Supernovae also have a cultural history, their brilliance etched in human records. In 1054, Chinese, Japanese, and Middle Eastern astronomers noted a guest star in the sky, bright enough to be seen in daylight. This was the Crab Nebula's supernova, its light traveling 6,500 years to reach Earth. In 1572, Tycho Brahe observed another, marveling at its sudden appearance, which challenged the idea of an unchanging sky. Johannes Kepler saw one in 1604, using it to argue for a dynamic universe. These events, recorded long before telescopes, show how supernovae have shaped both science and human wonder, their light a beacon across centuries. The physics of supernovae is a frontier of discovery. Scientists use supercomputers to simulate these explosions, modeling the collapse of a star's core and the shockwave that follows. These simulations reveal the complex interplay of gravity, nuclear reactions, and energy, showing how a star's death creates a burst of light and matter. Neutrino physics, a key part of these models, is studied in experiments like those at CERN, where particles mimic the conditions of a supernova's core. These studies help explain how elements are formed and scattered, a process that connects the smallest particles to the largest galaxies. Supernovae also influence their surroundings in unexpected ways. Their shockwaves can trigger the formation of new stars, compressing gas clouds in nebulae until they collapse under gravity. In the Carina Nebula, astronomers have seen young stars born in regions swept by supernova shockwaves, a cycle of renewal that keeps galaxies vibrant. These explosions also ionize gas, creating glowing regions that emit radio waves and X-rays. Telescopes like ALMA detect these emissions, revealing how supernovae shape the interstellar medium, the gas and dust between stars, like a painter adding color to a canvas. The elements from supernovae are essential for life. Carbon, oxygen, and iron, forged in these explosions, form the building blocks of planets and living things. Scientists study meteorites, which contain traces of these elements, to confirm their stellar origins. Some meteorites even carry prosolar grains, tiny specks of stardust older than the Sun, formed in ancient supernovae. These grains, analyzed with microscopes, reveal the chemical history of the cosmos, showing how supernovae seeded the galaxy with the ingredients for Earth and its life. It's a story of connection, where the death of a star gives rise to new worlds. Supernovae also produce rare isotopes, like nickel-56, which decay into cobalt and iron, powering the explosion's light. Astronomers observe this decay in the light curves of supernovae, which brighten and fade over weeks. These observations, made with telescopes like Swift, help scientists understand the explosion's mechanics and the elements it creates. Some supernovae, called pair instability supernovae, occur in extremely massive stars, leaving no remnant behind but scattering vast amounts of material. These rare events, seen in distant galaxies, are studied to understand the first stars in the universe, which shaped its early chemistry. As we linger in the glow of these cosmic fireworks, consider how supernovae bridge the past and future. Their light carries stories of ancient stars, while their elements build new worlds. Scientists continue to study them, using telescopes and simulations to unravel their secrets. Each supernova is a chapter in the universe's story, a moment of brilliance that shapes the cosmos. And as we prepare to drift to the next chapter, let's ponder the mysteries hidden within the universe's fabric, where secret pathways, like wormholes, might connect distant realms in ways we can only imagine. Breathe gently now, letting the quiet of the night cradle you like a soft, starlit wave. We've marveled at the dazzling supernovae, those cosmic fireworks that scatter light and elements across the universe, seeding new stars and worlds with their brilliance. Yet, within the vastness of the cosmos, there are mysteries that stretch beyond the light of stars, beyond even the pull of black holes. Picture a hidden pathway, a shimmering bridge woven from the fabric of space and time, connecting distant corners of the universe. These are wormholes, theoretical tunnels that might link far-flung realms, offering a glimpse of cosmic shortcuts through the universe's grand tapestry. Let's explore these elusive passages, where science meets imagination, and the universe whispers possibilities of worlds beyond our reach. Wormholes are born from the mathematics of Einstein's theory of general relativity, which describes how gravity bends the fabric of space-time. Imagine space-time as a vast, pliable sheet stretched across the cosmos, with stars and planets creating gentle dips in its surface. A wormhole is like a tunnel piercing through this sheet, connecting two distant points with a shortcut. Scientists call these structures Einstein-Rosen bridges, named after Einstein and his colleague Nathan Rosen, who first proposed them in 1935. Unlike black holes, which trap everything within their event horizons, wormholes are thought to have two open ends, like doorways leading to different parts of the universe, perhaps even to another universe entirely. These tunnels are purely theoretical, with no direct evidence yet, but they spark curiosity about the nature of space and time. The idea of a wormhole begins with the equations of relativity, which allow for solutions where space-time curves sharply, creating a bridge between two regions. Picture two cities on opposite sides of a mountain, connected by a tunnel rather than a long road around it. In the universe, these cities could be light years apart, separated by billions of years of travel at the speed of light. A wormhole might allow passage between them in an instant, defying the usual limits of distance. Scientists explore this concept through mathematical models, solving equations that describe how space-time might fold and connect. These models suggest that wormholes could exist, but they would require extraordinary conditions to form and remain stable, conditions that challenge our understanding of physics. One challenge is the stability of a wormhole. The mathematics shows that a wormhole's throat, the tunnel itself, would collapse almost instantly unless held open by a form of exotic matter. This matter would need negative energy or negative mass, properties that defy the rules of normal matter. Scientists hypothesize that quantum fields, like those described by quantum mechanics, might produce this exotic matter, creating tiny fluctuations of negative energy. Experiments at places like the Large Hadron Collider probe these quantum effects, searching for clues about whether such matter could exist. While no exotic matter has been found, the idea keeps wormholes alive in theoretical physics, a tantalizing possibility that pushes the boundaries of what we believe is possible. Wormholes also raise questions about time travel. Because space-time is woven together, a wormhole might not only connect distant places, but also different times. Imagine one end of a wormhole near Earth, the other near a black hole, where time slows due to intense gravity. If you pass through the wormhole, you might emerge in the past or future, depending on the time dilation at each end. This idea, explored by physicist Kip Thorne, suggests that wormholes could act as time machines, though they'd require precise control to avoid paradoxes, like meeting your past self. Scientists study these possibilities through thought experiments, using relativity to model how time and space might intertwine, like threads in a cosmic knot. The concept of wormholes also connects to black holes, but with a twist. A black hole's event horizon marks a point of no return, but some theories propose that certain black holes could have a wormhole at their core, leading to a white-holey hypothetical opposite that expels matter and light. Picture a black hole as a cosmic drain, pulling everything in, and a white hole as a fountain, pushing everything out. This idea stems from early solutions to Einstein's equations, but white holes remain speculative, with no evidence of their existence. Scientists use simulations to explore whether a wormhole could link a black hole to a white hole, creating a passage through the universe. These models are like sketches of a cosmic architecture we're only beginning to understand. Wormholes also inspire questions about the structure of the universe. Could they connect to other universes, part of a vast multiverse? Some theories, like string theory, propose that our universe is one of many, each with its own laws of physics. A wormhole might act as a gateway between these realms, a bridge across the cosmic ocean. Scientists explore this idea through mathematical models, imagining universes with different dimensions or constants, like bubbles floating in a higher dimensional space. While purely theoretical, these ideas draw on the same equations that describe our universe, suggesting that wormholes could be a key to understanding reality's deeper layers. Detecting a wormhole is a challenge, as they wouldn't emit light like stars or black holes. Scientists propose looking for indirect signs, like gravitational lensing, where a wormhole's gravity bends light from distant stars, creating unusual patterns in the sky. Another clue might be anomalous orbits, where objects move as if influenced by an invisible tunnel. Telescopes like the James Webb Space Telescope search for such effects, scanning the cosmos for hints of these hidden pathways. While no wormholes have been found, these searches push the limits of observation, encouraging scientists to refine their tools and theories, like explorers charting an uncharted sea. Wormholes also challenge our understanding of quantum mechanics. At the quantum level, particles can be entangled, sharing a connection that transcends distance. Some physicists, like Juan Maldacena, propose that wormholes might be linked to quantum entanglement, acting as physical bridges between entangled particles. This idea, called EREPR, suggests that wormholes and entanglement are two sides of the same coin, connecting the quantum world to the cosmic one. Researchers explore this through theoretical models, using quantum computers to simulate these connections, probing the boundaries between the very small and the very large. It's a poetic notion that the universe's smallest particles might hold the key to its grandest structures. The stability of wormholes also depends on the universe's geometry. Einstein's equations allow for different shapes of space-time: flat, curved, or even looped. A wormhole would require a specific geometry, like a saddle or a tube, to remain open. Scientists study these geometries through cosmology, using observations of the cosmic microwave background to determine the universe's shape. The Planck satellite suggests our universe is flat, but wormholes might exist in regions with unusual curvature, hidden from our view. These studies blend mathematics and observation, creating a picture of a universe that's both vast and intricate, like a tapestry with hidden folds. Wormholes also capture the imagination in science fiction, from stories of interstellar travel to portals to other dimensions. While these tales stretch beyond current science, they draw on real concepts, like Einstein's relativity and the idea of space-time as a flexible fabric. Scientists like Kip Thorne have worked with filmmakers, ensuring that depictions, like the wormhole in Interstellar, reflect accurate physics. In the film, the wormhole is a sphere, not a flat hole, a nod to how space-time curves in 3 dimensions. These collaborations show how wormholes bridge science and storytelling, inviting us to dream of cosmic journeys while grounding those dreams in theory. The study of wormholes also connects to the universe's energy. To keep a wormhole open, exotic matter would need to counteract gravity's collapse, possibly through negative energy. Quantum mechanics suggests that such energy exists in tiny amounts, seen in effects like the Casimir effect, where metal plates in a vacuum attract due to quantum fluctuations. Scientists experiment with these effects in labs, hoping to understand whether negative energy could stabilize a wormhole. While these experiments are far from creating a real wormhole, they reveal the strange interplay of quantum and cosmic forces, like a delicate dance at the edge of reality. Wormholes also raise philosophical questions about the universe's boundaries. If they connect to other universes, what lies beyond? Some theories propose a multiverse, where each universe has its own wormholes, like tunnels in a cosmic labyrinth. Others suggest that wormholes loop back within our own universe, creating shortcuts that defy distance. Scientists explore these ideas through cosmology and particle physics, using tools like the Large Hadron Collider to probe the fundamental nature of reality. These questions are like stars on the horizon, guiding our curiosity even if we can't yet reach them. As we linger in the mystery of wormholes, consider their place in the universe's story. They're not just theoretical curiosities, but windows into the nature of space-time, gravity, and quantum mechanics. Scientists continue to explore them through mathematics, simulations, and observations, seeking clues to their existence. Each equation solved, each model tested, is a step toward understanding the cosmos's hidden pathways. And as we prepare to drift to the next chapter, let's turn from these cosmic bridges to a closer wonder, the Moon, our celestial companion, whose origin ties us to the heart of our own planet's story. Breathe softly now, letting the stillness of the night wrap around you like a gentle lunar glow. We've wandered through the mysterious tunnels of wormholes, those theoretical bridges that hint at cosmic shortcuts across the universe's vast expanse. Now, let's bring our journey closer to home, to a familiar light in the night sky, a quiet companion that has watched over Earth for billions of years. Picture the Moon, its silvery face casting a soft radiance, a beacon that has shaped our tides, our myths, and our planet's story. The Moon's origin is a tale of cosmic collision, a dramatic embrace between Earth and a long-lost wanderer, whose fragments became our celestial partner. Let's explore the birth of the Moon, a story etched in ancient rocks and the silent dance of orbits, revealing a deep connection to our own world. The Moon's story begins some 4.5 billion years ago, when Earth was a young, molten planet, still cooling from its fiery birth. At that time, the solar system was a chaotic place, filled with wandering bodies left over from its formation. One such body, a protoplanet roughly the size of Mars, is thought to have collided with Earth in a cataclysmic event known as the Giant Impact Hypothesis. Scientists call this lost world Theia, named after the Greek Titan who birthed the moon goddess Selene. The collision was immense, releasing energy equivalent to 1 billion nuclear bombs, melting Earth's surface and flinging molten debris into orbit. This glowing ring of rock and magma, a mix of Earth's crust and Theia's remains, began to coalesce, slowly forming the Moon over thousands of years. Astronomers have pieced together this story using computer simulations, modeling how such a crash could create our lunar companion. The evidence for this violent birth comes from the rocks brought back by the Apollo missions. Between 1969 and 1972, astronauts walked the Moon's surface, collecting over 800 pounds of lunar samples. Scientists analyzed these rocks, finding they share striking similarities with Earth's mantle, the layer beneath its crust. The Moon's rocks contain forms of oxygen, isotopes, chemical signatures like cosmic fingerprints that match those found on Earth, suggesting a common origin. Yet, the Moon is lighter, lacking the heavy iron core that anchors Earth. This supports the idea that the Moon formed from Earth's outer layers, blasted into space by Theia's impact. These samples, studied with microscopes and spectrometers, are like letters from the past, telling the story of a collision that reshaped our planet. The giant impact didn't just create the Moon, it transformed Earth itself. The collision tilted our planet's axis, giving us the seasons we know today, as Earth wobbles gently in its orbit. It also sped up Earth's rotation, making days shorter in that ancient era, perhaps as brief as 6 hours. Over time, the Moon's gravity slowed Earth's spin through a process called tidal locking. where the moon's pull creates friction in Earth's oceans, gradually lengthening our days. Scientists study this interaction by measuring the moon's distance, which increases by about 1.5 inches each year as Earth's rotation transfers energy to the moon's orbit. Laser reflectors left by Apollo astronauts allow precise measurements, bouncing light back to Earth to track this slow drift. The moon's surface, scarred and silent, holds clues to its early history. Unlike Earth, with its shifting plates and weathering winds, the moon has no atmosphere to erode its craters. Its surface is a frozen record, preserving impacts from billions of years ago. Astronomers have studied these craters with telescopes and spacecraft, like the Lunar Reconnaissance Orbiter, which maps the moon in stunning detail. The largest craters, called basins, are vast scars from massive collisions during a period known as the Late Heavy Bombardment, about 4 to 3.8 billion years ago. The Mare Orientale, a basin over 600 miles wide, shows concentric rings formed when an asteroid struck, rippling the moon's molten surface like a stone in a pond. These features, visible in high-resolution images, reveal a violent youth when the moon was battered by debris in the early solar system. The moon's composition also tells us about its formation. Its rocks are rich in minerals like plagioclase, which floated to the surface as the moon cooled, forming a crust. Beneath lies a mantle, similar to Earth's but smaller, and a tiny core, perhaps only a few hundred miles across. Scientists study these layers using seismometers left by Apollo missions, which detected moonquakes caused by tidal stresses from Earth. These quakes, weaker than Earth's, suggest a rigid interior unlike our planet's molten core. The moon's low density, about 60% of Earth's, supports the idea that it formed from lighter materials ejected during the Theia impact. This composition, analyzed through lunar samples, paints a picture of a world born from Earth's outer layers, a fragment of our planet's heart. The collision that formed the moon also left it molten, a glowing orb of magma for millions of years. As it cooled, heavier materials sank, while lighter ones rose, creating the crust we see today. This magma-ocean hypothesis explains the moon's smooth, dark regions called maria, formed when lava flooded impact basins billions of years ago. Telescopes like the Lunar Reconnaissance Orbiter have mapped these maria, showing they cover about 16% of the moon's surface. Unlike Earth's volcanoes, driven by plate tectonics, the moon's volcanism was triggered by impacts, melting its interior and releasing lava. These flows, frozen in time, are like brushstrokes on a cosmic canvas, preserving the moon's fiery youth. The moon's influence on Earth goes beyond its origin story. Its gravity stabilizes our planet's axial tilt, keeping seasons predictable over millennia. Without the moon, Earth's axis could wobble chaotically, causing extreme climate shifts. Scientists model this stability using simulations, showing how the moon acts like a cosmic anchor, steadying Earth's orbit. The moon also drives tides, shaping our oceans and coastlines. These tidal forces, studied with satellites like GRACE, influence marine ecosystems and even early life, as tides may have mixed nutrients in ancient seas. The moon's gentle pull, measured through its gravitational field, is a quiet force that has shaped Earth's history. Water on the moon, once thought absent, adds another layer to its story. In 2009, NASA's L-Cross mission crashed into a lunar crater, detecting water ice in the debris. This ice, hidden in permanently shadowed craters at the moon's poles, likely came from comets that struck billions of years ago. The Lunar Reconnaissance Orbiter's instruments, like the LEND detector, found hydrogen in lunar soils, hinting at water-locked in minerals. Recent studies of Apollo samples revealed hydroxyl, a water-related compound, suggesting the moon's interior may hold enough water to cover its surface a meter deep. This discovery, made with advanced spectrometers, shows the moon is not as dry as once thought, a relic of its violent birth and cosmic collisions. The moon's formation also connects to the broader solar system. The giant impact hypothesis suggests that such collisions were common in the early solar system, shaping other planets and moons. Scientists study similar processes on Mars, where ancient craters hint at massive impacts, and on Mercury, where a thin crust suggests a violent past. Computer simulations model these collisions, showing how debris from impacts can form moons or rings around planets. The moon's unique origin, confirmed by its chemical similarity to Earth, makes it a key piece in understanding how rocky worlds like ours take shape, a story written in the scars and rocks of our lunar neighbor. The Apollo missions were pivotal in unraveling the moon's secrets. Astronauts like Neil Armstrong and Buzz Aldrin walked its surface, collecting rocks that revealed its age about 4.5 billion years, slightly younger than Earth. Radiometric dating, using uranium and lead isotopes, showed that the moon's crust formed soon after the Theia impact as molten debris cooled. These samples, studied in labs worldwide, also lack volatile elements like water, supporting the idea that the collision's heat vaporized lighter materials. The Apollo data, combined with modern spacecraft like India's Chandrayaan missions, provide a detailed picture of the moon's birth, a violent yet creative moment in our planet's history. The moon's orbit, elliptical and slightly tilted, also holds clues to its past. Scientists use laser ranging, bouncing beams off Apollo reflectors, to measure its distance with millimeter precision. This shows the moon drifting away, a slow dance driven by tidal forces. Over billions of years, this drift has shaped Earth's rotation and the moon's own tidal locking, where one side always faces us. This phenomenon, studied through orbital mechanics, explains why we never see the moon's far side, a hidden landscape mapped by spacecraft like China's Chang missions. The far side, rugged and cratered, contrasts with the near side's smooth maria, a difference that hints at an uneven cooling after the moon's formation. The moon's birth also raises questions about its companion, Theia. Was it a rocky world like Mars, or something else? Simulations suggest Theia was similar to Earth in composition, with a mix of rock and iron. Its collision angle, likely oblique, determined the moon's size and orbit. Scientists explore these details with supercomputers, modeling how Theia's impact melted Earth's surface and ejected debris. Some theories propose that Theia's remnants are buried deep in Earth's mantle, detected as anomalies in seismic data. These studies, blending geology and astronomy, show how the moon's birth is a piece of Earth's own story, a shared history written in stone. The moon's influence extends to human culture, its light inspiring myths and calendars across civilizations. Ancient peoples saw it as a goddess, a guide, or a marker of time. Scientists study these connections through archaeoastronomy, finding lunar alignments in structures like Stonehenge. The moon's cycles, measured with precision today, shaped early human understanding of the cosmos, a reminder of its quiet presence in our lives. Its origin, confirmed by science, transforms these myths into a story of cosmic creation, where a collision billions of years ago gave us a partner that still shapes our world. As we linger in the moon's gentle light, consider how it ties us to the cosmos. Its rocks, its craters, its orbit tell a story of Earth's youth, a time of fire and chaos that gave birth to a serene companion. Scientists continue to study the moon, with missions like Artemis planning to return humans to its surface, seeking new clues about its formation. Each discovery is a chapter in the story of Earth and Moon, a tale of connection across billions of years. And as we prepare to drift to the next chapter, let's look beyond our lunar neighbor, to distant worlds that might mirror Earth, waiting like gardens in the cosmic night. Breathe gently now, letting the quiet of the night wrap around you like a soft, starry veil. We've lingered in the silvery glow of the moon, our celestial companion born from a fiery collision with Earth, a piece of our planet's heart orbiting in the cosmic night. Now, let's drift beyond our lunar neighbor, casting our gaze across the vastness of the universe to search for other worlds' distant planets that might mirror Earth's beauty, cradling oceans and life beneath alien skies. Picture a sea of stars, each one a sun with its own family of worlds, some rocky and serene, others swirling with gas or ice. This is the quest for Earth-like planets, oases in the cosmic desert where water flows and life might thrive. Let's explore this search, guided by telescopes and curiosity, as we seek out gardens in the stars, whispering possibilities of life beyond our own. The search for Earth-like planets, or exoplanets, began in earnest in the 1990s, when astronomers first confirmed planets orbiting stars beyond our Sunday. These worlds, found in distant solar systems, range from scorching gas giants to rocky orbs that might resemble Earth. The key to finding an Earth-like planet lies in the habitable zone, a region around a star where temperatures allow liquid water to exist, a crucial ingredient for life as we know it. Imagine a cosmic Goldilocks zone, not too hot, not too cold, but just right for water to pool on a planet's surface. Scientists use telescopes like NASA's Kepler Space Telescope, launched in 2009, to hunt for these worlds, scanning the light of thousands of stars for the faint signals of planets passing in front of them, a phenomenon called a transit. A transit occurs when a planet crosses its star, causing a slight dip in the star's brightness. Picture a tiny shadow flitting across a distant candle, noticeable only with the sharpest eyes. Kepler observed over 100,000 stars, detecting thousands of exoplanets by measuring these dips. Some, like Kepler 186f, orbit in their star's habitable zone, about 500 light-years away. This planet, roughly Earth-sized, circles a red dwarf star, cooler than our Sunday, suggesting it could have liquid water. Astronomers analyzed transit data with spectrographs, breaking starlight into colors to reveal a planet's size and orbit. These observations, refined by computers, show that Earth-sized planets in habitable zones are more common than once thought, scattered like seeds across the galaxy. Not all stars are ideal for hosting Earth-like worlds. Massive stars called supergiants burn too brightly and die too quickly, leaving little time for life to evolve. Red dwarfs, the most common stars in the galaxy, are smaller and cooler, living for tens of billions of years. Their habitable zones are closer, meaning planets must orbit tightly to stay warm enough for water. However, these close orbits can tidally lock a planet, with one side always facing the star, creating extreme temperature differences. Scientists study planets like those in the TRAPPIST-1 system, 40 light-years away, where 7 Earth-sized planets orbit a red dwarf, 3 in the habitable zone. Telescopes like the James Webb Space Telescope probe their atmospheres, searching for signs of water vapor or gases like oxygen that might hint at life. The atmospheres of exoplanets are key to their habitability. When a planet transits its star, some starlight passes through its atmosphere, absorbing specific wavelengths that reveal its composition. Imagine sunlight filtering through a stained glass window, each color telling a story. Spectrographs on telescopes like Hubble and James Webb detect molecules like water, methane, or carbon dioxide, which could indicate conditions suitable for life. For example, the planet K2-18b, 120 light-years away, showed signs of water vapor in its atmosphere, sparking excitement about its potential. Scientists use these observations to model whether a planet's atmosphere could support liquid water, a delicate balance of pressure and temperature shaped by the planet's distance from its star. Finding an Earth-like planet requires more than just water. A planet needs a magnetic field to shield it from stellar radiation, much like Earth's magnetic field protects us from solar winds. Without this shield, a planet's atmosphere could be stripped away, as happened on Mars, leaving it dry and barren. Scientists study exoplanets' magnetic fields indirectly, looking at their star's activity and the planet's composition. Rocky planets with molten cores, like Earth, are more likely to generate magnetic fields. The James Webb Telescope's infrared observations help identify rocky planets, distinguishing them from gas giants or ice worlds, narrowing the search for Earth-like conditions. The diversity of exoplanets is staggering. Some, called hot Jupiters, are massive gas planets orbiting close to their stars, with temperatures exceeding 1,300 degrees Celsius. Others, like super-Earths, are rocky but larger than Earth, with stronger gravity that might shape unique landscapes. Mini-Neptunes, with thick atmospheres of hydrogen and helium, blur the line between rocky and gaseous worlds. Scientists categorize these planets using data from telescopes like TESS, the Transiting Exoplanet Survey satellite, which has found over 7,000 candidate planets since 2018. Each discovery adds a piece to the puzzle, showing that planetary systems are as varied as the stars they orbit, a cosmic gallery of worlds waiting to be explored. The search for life focuses on biosignatures, chemical signs that suggest biological activity. On Earth, life produces gases like oxygen and methane, which could be detected in an exoplanet's atmosphere. Imagine a planet with air rich in oxygen, a whisper of life carried across light years. Scientists use spectroscopy to search for these gases, though distinguishing biological from geological sources is challenging. For example, volcanic activity can produce methane, mimicking life's signature. The James Webb Telescope, with its sensitive instruments, is designed to detect such biosignatures, scanning planets' in habitable zones for clues that life might exist, from simple microbes to complex ecosystems. One promising system is Gliese 581, 20 light-years away, where astronomers found several planets, including Gliese 581d, orbiting at the edge of the habitable zone. This planet, 7 times Earth's mass, might have a thin atmosphere and icy surface, resembling a larger Mars. Its star, a red dwarf, provides just enough warmth for liquid water if the planet has a greenhouse effect. Scientists study such worlds with ground-based telescopes, like those in Chile, measuring their orbits to estimate their potential for life. While Gliese 581d is too cold for Earth-like conditions, it sparks hope that similar planets, with just the right balance, might exist nearby. The Kepler mission revealed that billions of planets likely exist in our galaxy's habitable zones. By surveying a small patch of sky, Kepler estimated that 1 in 5 Sunday-like stars hosts an Earth-sized planet in the habitable zone. With over 100 billion stars in the Milky Way, this suggests millions of potential Earths. Scientists refine these estimates with statistical models, combining transit data with stellar surveys. The sheer number of possibilities, like stars in a summer sky, suggests that Earth-like worlds are not rare, but scattered across the galaxy, waiting for our telescopes to find them. The search also involves studying our own solar system for clues. Planets like Mars, with its ancient riverbeds, and Jupiter's moon Europa, with its subsurface ocean, show that habitable conditions can exist beyond Earth. Scientists use rovers, like Perseverance, to explore Mars for signs of past life, while missions like Europa Clipper, planned for the 2030s, will probe its icy crust for water. These studies inform exoplanet research, showing what conditions life might need: water, energy, and stable chemistry. The Cassini mission to Saturn's moon Enceladus found water jets, hinting at subsurface oceans, a reminder that life's potential extends beyond planets to moons, broadening our search. Exoplanets challenge our understanding of planet formation. In our solar system, rocky planets like Earth formed close to the Sun, while gas giants like Jupiter formed farther out. Yet, many exoplanets defy this pattern, with hot Jupiters orbiting closer than Mercury or super-Earths in habitable zones. Scientists model these systems with simulations, showing how planets migrate inward or outward as they form, pushed by the gravity of disks or companion planets. The Atacama Large Millimeter Array observes these disks around young stars, revealing rings and gaps where planets are born, like footprints in cosmic dust. These observations help explain the diversity of exoplanets, each a unique story of formation. The search for Earth-like planets also involves new technologies. The Extremely Large Telescope, under construction in Chile, will use adaptive optics to sharpen images, detecting faint planets around bright stars. Space missions like Ariel, planned for 2029, will analyze exoplanet atmospheres in detail, searching for biosignatures. These tools, combined with artificial intelligence, analyze vast datasets, identifying planets that might otherwise be missed. The future of exoplanet research is bright, with telescopes pushing the limits of what we can see, like lanterns illuminating the cosmic night. The possibility of life elsewhere raises profound questions. If we find an Earth-like planet, what would its life be like? Could it host creatures as complex as humans, or only simple microbes? Scientists explore these questions through astrobiology, studying extreme life on Earth, like bacteria in deep-sea vents, to understand what might thrive elsewhere. Planets with water and stable climates, like those in the TRAPPIST-1 system, are prime targets, their atmospheres probed for signs of life. The search is not just about finding planets, but understanding what makes life possible, a cosmic quest that ties us to the stars. As we linger in this search for cosmic oases, consider the vastness of the galaxy. With its billions of stars and countless worlds, each planet is a possibility, a garden waiting to be discovered. Scientists continue their quest with telescopes and missions, each discovery a step toward answering whether we are alone. And as we prepare to drift to the final chapter, let's reflect on this journey through the universe, from its fiery birth to the distant worlds that might hold life, a story that cradles us in wonder as we slip towards sleep. Breathe softly now, letting the quiet of the night wrap you in a gentle embrace, like the glow of distant stars. We've journeyed far, from the cosmic oases of Earth-like planets to the radiant birth of our moon, each step revealing the universe's wonders, from its fiery origins to the possibility of life among the stars. Now, as our voyage through the cosmos draws to a close, let's pause to reflect on this grand tapestry of light, matter, and mystery. Picture yourself floating in a sea of stars, each one a story, each story a thread in the universe's great narrative. This is our moment to weave together the threads of our journey, to marvel at the beauty of the cosmos, and to let its wonders carry you into a peaceful, restful sleep. Let's drift through this final chapter, a quiet celebration of the universe's secrets, as we bid the night farewell. Our journey began with the Big Bang, a singular moment 13.7 billion years ago, when a tiny spark blossomed into the vast universe we know today. From that first burst of light and energy, space and time unfurled, setting the stage for all that followed. Scientists uncovered this origin story through the faint glow of the cosmic microwave background, a whisper of light that still fills the sky, captured by telescopes like Planck. This light, stretched across eons, revealed a universe born in simplicity, with hydrogen and helium as its first elements, ready to form the stars that would light the cosmic night. It's a story of beginnings, where the smallest seed grew into a cosmos of unimaginable scale, a reminder that even the grandest things start with a gentle spark. From those early elements, stars were born in glowing nebulae, cosmic nurseries where gravity wove gas and dust into radiant beacons. These stars, like our Sunday, became forges, fusing hydrogen into helium, then heavier elements like carbon and oxygen, the building blocks of planets and life. Astronomers have peered into these nurseries, like the Orion Nebula, with telescopes like Hubble, watching stars ignite in clouds of shimmering gas. Each star's birth was a moment of creation, a light that warmed the darkness, scattering elements that would one day form worlds like ours. The story of stars is one of transformation, turning the universe's raw materials into the ingredients for everything we see and touch. Yet, stars are not eternal. The most massive among them end their lives in spectacular supernovae, explosions that outshine galaxies and scatter heavy elements like iron and gold across the cosmos. These cosmic fireworks, observed through telescopes like Swift, leave behind neutron stars or black holes, while their elements seed new stars and planets. The Crab Nebula, born from a supernova seen in 1054, glows as a testament to this cycle, its light captured by Chandra's X-ray eyes. Supernovae are the universe's artists, painting the galaxy with the colors of life, connecting the death of one star to the birth of new worlds. Some stars, in their final moments, collapse into black holes, enigmatic regions where gravity bends space-time so deeply that even light cannot escape. These stellar mass black holes, detected through their glowing accretion disks and powerful jets, are scattered throughout our galaxy, perhaps millions in number. Scientists use X-ray telescopes like Chandra and gravitational wave detectors like LIGO to find them, revealing their silent influence. Black holes are like cosmic shadows, their presence felt through the dance of stars and gas, a quiet force that shapes the galaxy's rhythm, a mystery that deepens our wonder at the universe's complexity. At the hearts of galaxies, supermassive black holes reign, giants millions or billions of times the sun's mass, orchestrating the orbits of stars and gas. In our Milky Way, Sagittarius A holds court, its mass measured by the swift orbits of nearby stars, tracked by telescopes like Keck. Across the universe, these black holes power quasars and jets, shaping galaxies with their energy, as seen in the glowing image of M87's black hole, captured by the Event Horizon Telescope. Their story is one of power and balance, guiding the growth of galaxies like conductors of a cosmic symphony, their influence felt across billions of light years. These galaxies, in turn, weave together in the cosmic web, a vast network of filaments, walls, and voids that spans the universe. Gravity and dark matter sculpt this structure, with galaxies clustering like pearls on a string, as mapped by the Sloan Digital Sky Survey. The web's filaments, glowing with starlight, stretch across millions of light years, while voids lie silent, vast and empty. This cosmic architecture, born from the Big Bang's ripples, reveals a universe of connection, where every star, every galaxy, is part of a larger whole, a tapestry woven by the patient hand of gravity. We pondered the possibility of wormholes, theoretical tunnels through space-time that might connect distant realms or even other universes. Born from Einstein's equations, these bridges remain unseen, but scientists explore them through mathematics and simulations, searching for signs in the bending of light or the orbits of stars. Wormholes are like whispers of possibility, inviting us to imagine a universe where space and time fold in unexpected ways, a cosmic labyrinth waiting to be explored, its secrets hidden in the equations of relativity. Closer to home, we trace the moon's birth, a story of a colossal collision that forged our celestial companion from Earth's own substance. The Apollo missions brought back rocks that told this tale, their chemistry matching Earth's mantle, a testament to a shared origin 4.5 billion years ago. The moon's craters and maria, mapped by spacecraft like the Lunar Reconnaissance Orbiter, preserve a record of its violent youth, while its tides shape Earth's oceans and life. This story ties us to our planet's past, a reminder that even our closest neighbor is a piece of the cosmic puzzle. Our journey ended with the search for Earth-like planets, worlds where water might flow and life could thrive. Telescopes like Kepler and James Webb scan the stars, finding planets in habitable zones, their atmospheres probed for signs of water or oxygen. Systems like TRAPPIST-1, with its Earth-sized worlds, spark hope that life might exist beyond our solar system, a possibility that fills the cosmos with wonder. This search is a quest for connection, a dream of finding other gardens in the vast desert of space, each planet a story waiting to be told. Now, as we reflect on this journey, consider the universe's beauty, a symphony of light and matter played across billions of years. From the Big Bang's spark to the glow of distant planets, each discovery is a note in this cosmic melody, a reminder of the universe's vastness and mystery. Scientists, with their telescopes and equations, are like storytellers, weaving tales from the light of stars and the whispers of ancient radiation. Their work connects us to the cosmos, showing that we are not separate, but part of its story, made of the same elements forged in stellar fires. The universe is a place of wonder, where every star, every planet, every black hole holds a secret waiting to be uncovered. It's a story that began with a single moment and continues to unfold, carried by the light that reaches us across eons. As you rest here, let these stories cradle you, like a lullaby sung by the stars. If you've enjoyed this journey, consider leaving a comment to share where you're listening from, what time it is in your corner of the world. Your voice, like a star's light, adds to the universe's tale, a quiet connection across the night. Let the cosmos be your guide as you drift towards sleep, its mysteries a gentle backdrop to your dreams. Picture the stars above, each one a light that has traveled for millennia to reach you, carrying stories of creation and possibility. The universe is vast, but in this moment, it feels close, a comforting presence that wraps you in its glow. As you close your eyes, let the wonders of the Big Bang, the stars, the black holes, and the distant worlds linger in your mind, a soft tapestry of light and mystery. Sleep well now, carried by the quiet rhythm of the cosmos. Let the universe's stories weave through your dreams, a gentle reminder that you are part of something grand, something timeless. Good night, and may your dreams be filled with the beauty of the stars, the whispers of creation, and the endless wonder of the universe.